Guess we can start.
Okay, yeah, it's just on time.
Yes, so we are very happy to have Jesper here. Thank you for coming at such an early time. And the talk will be about the group function in critical loop models.
Okay,
Yeah.
thank you very much. Thanks for the very nice invitation. It's a great pleasure to be back at IHES. I stayed here for 6 months during COVID, and that was a slightly unhappy experience because there was not so many people around. But so anyway, so this seed seminar series, of course, is on spanning trees and forests. And you will see in the end of this talk how this subject that I have picked here is related to that overarching topic. So there's a number of collaborators who need to be credited here. Max Downing, Linnea Grant-Samuelson, Yassine Idlev, Frank-Ram Nives-Vivat, Sylvain Rivaud, Paul Roux is here, Hubert Saleur, and Kai Wiese, who will also be mentioned. Which brings me to the next topic, how to move to the next page. Okay.
Your laptop.
Well, now this is completely frozen.
Because you are on the Zoom.
Okay, no, but with 2 fingers I can do it. Okay, so great. Okay, so there are 2 ways to present this topic via 2 different models. One is the Q-state post model, and the other one is the ON model. And both are perfectly possible, and both have been followed through in all our recent papers. So you just have to pick a choice of presentation and stick to it. So in the main part of the talk, I'll focus on the ON model. But I thought I would just start out with some general overview saying how the 2 models are somehow sharing features that are very similar but a little bit different. And that will permit us to treat both models. So let's start from the Q-state pods model. So originally it's formulated as a model of Q-state spins. So that sounds like something that would require Q to be a positive integer. And interactions, they have an SQ permutation symmetry. However, you can get rid of this constraint of having Q integer by moving to an equivalent loop model that is defined on a medial lattice. I should have said that I work in 2 dimensions via some trick due to Baxton, Kelland, and Wu. It turns out that this loop model has some extra symmetry that was exploited by Paul Roux, who is here. That's called PSUN. It's also related to an integrable model, a 6-vertex model, and it's related to an algebra, which is the Temperley-Lieb algebra. Okay, so also for the ON model, you have a similar content, but with all of these objects just being slightly different. So now it turns out that the permutation symmetry commutes with the partition algebra in general dimension. And if you move down to 2 dimensions, the object of relevance that is having the symmetry, carrying the symmetry, is the Potts-Temperley-Lieb algebra, which is some variant of the Temperley-Lieb algebra, as you will understand. So now, moving down to the ON model, you see that it has a very similar setup. Originally, n needs to be an integer because we treat vector spins living in n dimensions. But you can turn it into an equivalent loop model after a little modification that will appear in the next slide and be recalled. Also, in that model, you have integrability underlying because it's related to a 19-vertex model now, sort of a spin 1 version of the 6-vertex model. And instead of the Temperley-Lieb algebra, you are having an object that's called the Motzkin algebra. And again, ON commutes with some kind of partition algebra, which is called now the Brouwer algebra. And if I move from general dimension down to 2, it becomes to be very specific, the unoriented Jones-Temperley-Lieb algebra. And this has some consequences for the treatment of symmetries in this model. So, so the point is that for each of these models, we have results which are extremely closely related but slightly different. And I'll just focus on the ON model to show you one set of results. But to return to the subject of this seed seminar series, to get to random forests and random trees and fermionic field theories, what I could do in the end is to take the Potts model and send Q to 0, so as to get uniform spanning trees. And you will see that in that context, the predictions of this talk are going to be highly non-trivial. So, you know, in math or even in physics, it's always a good idea to work in the correct generality. And the correct generality is to treat the whole ON or Q-state Potts model at once. So, okay, here is the ON model. I hope this is not too surprising. So we start from hexagonal lattice. We could take a square lattice if you want, but the hexagonal lattice is even nicer. You throw down loops on this lattice and you give each one a non-local weight n. In addition, there's a local weight k for each step that you take on the lattice. So if you look at a little surrounding of one vertex, and if you count each incoming edge as 1/2 edge, you will see that the empty vertex should have weight 1. A filled-in vertex should have weight k, because it has 2 half edges, which is 1 edge. And then in addition, there's this extra edge per loop. So the partition function is k to the power number of steps, monomers, and n to the power number of loops. And if somehow I wanted to make sure to sum over all configurations, I could think of this lattice as being built up by a small R-like matrix that will take 2 ends and go through 2 vertices and turn them into 2 outgoing ends. So time moves upwards. And then you would have to go through 8 configurations of a pair of vertices, given these weights. So that gives us access to the algebraic formulation of this model. Okay, so here's the partition function again. Now, it turns out that to get a conformal field theory, to get a critical model, you need to specify a convenient value of k. So physically, maybe you could imagine that you start with taking k very small. So the lattice is basically empty. And then you crank up k a little bit, and then there will be more and more stuff on the lattice. And provided that n sits between -2 and +2, there is such a critical value for k so that the size of the largest loop will diverge. Okay, so this value is called kc, and it takes the value of this expression here with the, I always get this wrong, the plus or the minus sign. That must be, I want the smallest value of k, so I want the minus sign. Okay, and if k is beyond that value, you will get into another phase, which is called the dense phase. But inside that dense phase, there is another, there's an integrable point, which describes the whole phase. So any k larger than kc and less than infinity is described with this kc with the other value of the sign. So, okay, so that's a very neat model. So it has a dense and a dilute phase, and you can vary n between -2 and 2. And taking n to specific values, you can get all kinds of interesting models of interest. So yeah, interesting models of interest, that was a good one. So the n equals to 1 dense phase is side percolation. N equals 1 dilute is the Ising model. If you take n goes to 0 in the dilute phase, you get self-avoiding walks. And if you take n equals to 2, you will get the XY model, or a Gaussian free field. And then here in red, I again pay lip service to the subject of the seminar series, if you did the same kind of stuff for the Potts model as a loop model, and if you take the number of states to 0, then you will get uniform spanning trees. So that would be like almost like n goes to 0 in the dense phase here. But as you have guessed from the first slide, the operator content is just a slightly little bit different. But nevertheless, results will apply if we take that limit in the ON model.
If you take n between 1 and 2, would you get all the other normal?
Yeah, sure. I will do that. I can do that. So I can get the series of minimal models both on the dilute and on the dense branch. Now, there's an important point, of course, which is that once we have admitted this non-local setup in which there's a non-local loop weight, we are giving access to some observables which are not there in the minimal models. Okay, so really, most of these points here, they correspond to logarithmic CFTs. And actually, there is even something logarithmic going on in this model, even when n takes generic values.
But it's also beyond what minimum model and its twisted sector.
Yes. But you can somehow quotient out at specific values of n corresponding to roots of unity cases. You can quotient out some of this non-local stuff, and then you can actually get the honest to goodness minimal model. So you could get, for example, that Ising model at n equals to 1 dilute, but then you would just have to disallow certain observables that I will define later on. So most of this is handled just by continuity. So in particular, the 3-point structure constants that I'm going to talk about, they will not really change when I set n to specific values. But what I will do is to stay clear here of logarithmic CFTs, and I'll treat the case of generic n, where there is no root of unity stuff involved. So, of course, the conformal field theory of the ON model is very well known. It has been investigated by many people in the 80s. I should also cite Bertrand, of course. There is one particular paper that I have looked at here. That's the one that's called Coulomb gas approach to something from 87. And so looking up results in that paper, but which sort of came about by a joint effort. Many people in Saclay were aware of these results simultaneously. It turns out that if I parameterize the central charge by this beta, like this, then there are 3 types of operators in the model. So the operators, they are going to be specified, of course, by their conformal weights, delta and delta bar for the holomorphic and anti-holomorphic part. Those I will package into something that I will call momentum P. And the momentum P will be parameterized by R and S, so that looks like cat's labels. And they are, except that they will not necessarily be integer. And the cat's labels, they couple to R and S. And then now I can specify 3 types of fields with this notation. So the first kind of field is like generalized energy operators. So they are degenerate fields. So they span cat modules. So they have one singular vector at level S. They have R equals to 1 and S equals to an odd integer. If it was the Potts model, it would just be any positive integer. So that's one slight difference. There's another kind of field that I will call a diagonal field. So it's truly diagonal. It has the same left and right conformal dimension. It has 0 spin. And it's characterized by any complex momentum. And the last kind of field that's the most interesting in my point of view, it's called a non-diagonal field. It has R and S labels, so that R is half an integer. and S is such that R times S is an integer. In fact, R times S is the spin. And you see this thing here has a different holomorphic and anti-holomorphic weight. So this is a more complicated field than the others. And now in the loop model, all of these three types of fields, they have some interpretation. So the degenerate field I already touched on, that's the integer field and its generalization. So epsilon, epsilon bar, epsilon double prime, and so on. The diagonal field has the following interpretation. If I insert it in some point, then it will modify the weight of loops that run around that point. So there is some easy formula that gives me the weight that depends on this momentum for a loop that turns around that point. So in general, that could be even a complex weight. And the non-diagonal field has the interpretation that it inserts 2 times R open loop segments. This is why R needed to be half an integer. So that number of loop segments is then integer. And the S variable is saying something about what happens if, for example, the last of these loop ends starts moving around the insertion point and goes over to the other side in front of the other R-1 loop ends. Then it's going to get a complex phase factor that is exponential IS times theta, the angle that it winds around. And and then let's just notice again that the energy operator is this degenerate V1,3 field. So this model has a CFT limit just provided that this energy field is irrelevant. So that gives me a very large range of beta values for which the model is a CFT. Okay, let's move to correlation functions. So on this picture here, I simply ask my computer to flip a coin for each hexagon on a tiling of the plane. And it's a fair coin. So if the coin is up, it's white, and if it's down, it's black. And then in addition, to show you where the loops are living, I just drew the contours separating black and white. Those are the loops. Okay, so this is the dense n equals to 1 loop model. And then I also placed 3 points a little bit at random. And one question that I could ask is, do those 3 points belong to the same loop? So here I cheated just a little bit by positioning those points because I chose them to actually be on the same loop, which is an unlikely thing to happen, okay? So what I want to do is to ask the probability that this happens. So let's call that P of Z1, Z2, Z3 being on the same loop or the same hull. Of course, by global conformal invariance, the dependence of the coordinate is known. But what is not known is the structure constant. If I have normalized properly my 2-point functions, then I have normalized my fields, and then I have no normalization to play on anymore. So there's a structure constant C222. So why do I call it C222? Okay, I call it C222 because if you look at this little green environment here, you see that there are 2 loop strands that go out of that environment. And those 2 loop strands, they will not contract among themselves when I go away from that point. They will move on to some of the other points. And you can see there's only one thing that can happen. The only thing that can happen if I insert 2 legs, 2 legs, and 2 legs, and if they cannot self-contract, is that they will contract in such a way that the 3 points will belong to the same loop. It's known, and that is where Hubert Saller and Bertrand Duplantier should be credited. It's known that this exponent delta is equal to 1/8. And now the goal is to find out what is C222.
So sorry, in the language before, which operator is this? It's one of those guys with 2 legs, but it's the non-diagonal field, or it's one of the degenerate fields?
It's non-diagonal, but there are two choices for this non-diagonal field because there's this phase still. It could be the one. Sorry. Okay. So it could come with this phase when one of the legs turns around. Okay, so there could be a minus sign or there could be a plus sign. So in this case, it's a plus sign.
It's H10. Yes, it's the one for the here, it's just H10.
Yes.
And S.
So it's 1,0. Yes. Okay. Of course, everybody could have some obsessions or psychological problems or strange dreams. Okay, so here's a strange dream that could come, that could dawn upon you. Okay, so you could think, okay, let's take some arbitrary Riemann surface. Let's ask that some loops turn around some of the handles. Let's put in some points here that will modify the weights of loops that turn around them. Let's put in some small environments that spit out 4 legs or 6 legs or 1 leg or 3 legs and let them connect up in some way. And let's ask what's the probability that all of this happens. Okay, so this is, as any dream, it could sort of move closer or further out of reality. But the point is here that the open curves here, they define what we will call a combinatorial map. I'll come back to it a little bit later. Mathematicians actually want to construct the probability measure for loop models. And so they think a lot about the Siegel axioms. So there are basically 3 building blocks to be understood if you want to treat arbitrary Riemann surfaces. You need an annulus with 1 operator insertion, a disk with 2 insertions, and a pair of pans. And then the blocks, they will be glued together somehow by integrating over eigenstates of some evolution operator. And of course, I can also share this dream. And now the dream will crash down in this talk, at least to dealing with 3 points on a sphere. So the progress, generally speaking, this far, is that so the fields that I discussed, they are related to, on the lattice, to irreducible representations of this unoriented Jones-Temperley-Lieb algebra. And we have actually a bijection between correlation function and combinatorial maps. So that means that when you make a drawing, such as the drawing that 3 points belong to one same loop, this is actually like a correlation function. There's conformal symmetry, but we have also understood that it is an enhanced version of conformal symmetry, not in the sense of an extended conformal symmetry, but somehow enhanced to something that we call interchiral symmetry. And that goes via this energy operator V13. It can somehow be used to shift the second Katz label in a way that will glue together conformal blocks into larger conformal blocks that we call interchiral blocks. And that is important for treating efficiently this theory. And then in addition, we have this global ON symmetry, which we somehow believe has been overlooked for way too long. It was there in the definition of the model, but somehow it's important to see that we have not only CFT, but we also have this global symmetry to take into account.
And this is for generic.
For generic N. So ON then has to be understood in the sense of a delinear category. Okay, so the story of critical exponents, that's the story of 2-point functions. So that is the 1980s. And the 3-point functions, that's what I'm going to focus on, but I will also touch a little bit on n equals to 4. That makes intervene ideas of conformal bootstrap, in which case we have partial but not complete analytical control yet. So now for the 3 classes of operators, the 3-point functions, they were well understood for degenerate operators back in the 1980s by Dotsenko and Fateev. So their work on minimal models can basically extend it by analytic continuation to any value of the loop weight, but only for this class of operators. if you want diagonal operators, well, then with Yassin and Hubert in 2016, we made a conjecture that in general this is related to the DOZZ, so Dawn Otto twice Samologikov formula for an imaginary version of Liouville quantum gravity. And this precise result was generalizing earlier work by Delfino and Iti and others, Marco Pico, Raul Santachiara. And now in 2024, 4 probability theorists from the Beijing group, they actually proved this result. So it's a theorem now. So the main point that I'm going to tell you today is that for non-diagonal operators, now we also know this 3-point structure constant. And there is one thing that needs to be mentioned, that is that the precise, just the one case that I showed you here with 2 legs, 2 legs, 2 legs, this was actually also proved by the probability theorists. And it played some role in getting us to the full result. So the way that this progress has been possible is to work both on the CFT and on the lattice model. So the lattice model is constructed in general by using some partition algebra. So you want to make your system move forward in time. So you have 2 time slices, one fixed at time 0 and another one advancing at time t. And you want to see how via non-local objects such as clusters and loops, how those 2 time slices are partitioned into sets. So this is shown here. So if you want the most general model of clusters that can cross, you will need this kind of algebra. It's generated by, 3 kinds of generators. A thing that detaches one point, a thing that glues together 2 neighboring points, and a permutation operator. But for dealing with loop models, we are only interested in a very small subset of generators, which are given like this. They tie together 2 neighboring points via some arc on the top and the bottom, and that's the famous Temperley-Lieb algebra. Now we need to make this model, this algebra, periodic to deal with the bulk theory. So it's very important here to deal with the bulk and not the boundary theory. So we need an extra periodic generator, and we also need some shift operator. And so that together that defines what is called the periodic or affine Temperley-Lieb algebra. And you see that if you start multiplying these generators, you will get states of this type. So you will have some arcs, and then you will have some lines that go through the system up to some time t. And we need to define an object that I will call the pseudo-translation. So the pseudo-translation is obtained by sort of declaring the same points to be part of through lines, but shifting the through lines 1 step towards the right. So you see, you don't shift the whole state, you just shift towards the right, how the bottom 3 points are linked to the top 3 points. Okay, and so why is this important? Well, it's important because this periodic algebra is infinite dimensional. After all, these through lines, they could just keep spiraling around your system any number of times. So if you want a finite dimensional algebra for finite width, you will need some way to tame this. And one way of taming it is to say that once all the lines have moved around the system, you will just declare that to be the identity. You could do slightly better. You could claim maybe that you want them to rotate 7 times before you declare it the identity, but let's keep things simple here. So t to the 2r is set to 1. So this is a quotient. And then the algebra is represented by something that's called standard modules, which are irreps of the algebra, and they are spanned by link patterns, which look like one half state. So the through lines have sort of been cut through. And what is the basic property of these representations is that T acts as e to the pi is. So you see now, the thing that is really important here is that those R and S labels that I had in the CFT, I also have them on the lattice. So R2R was the number of defect lines, and S is this momentum like eigenvalue when those lines, they turn around the periodic direction. And they just carry over directly to the CFT. Okay, the next thing I want to explain is what is a combinatorial map. So a combinatorial map, that's our way of encoding a correlation function because we can show this bijection. So it's a connected graph along with a cyclic permutation of the half edges that come out of each vertex. So so you can sort of train yourself on this little picture. Suppose you have 4 points, 3 points that spit out 1 leg, 1 point that spit out 3 legs. If you somehow just turn that point around so that you make a cyclic permutation of the way in which legs are connected to the other points, you get something that looks different, but which is the same. But if it is not related by a cyclic permutation, then you could get something else, and that would be declared to be another combinatorial map. And also, you cannot have 2 legs that come out and just self-contract like a small loop. If you want this, they have to go at least around some other point. And you should not forget that we are on a sphere. So everything that looks like it's turning around something, you could wrap it around and make it turn around the remainder of what you have. So in the case of 3 points, the situation is very simple with these non-diagonal operators that we have, because for each choice of fields, this combinatorial map is simply unique. There is just one. Here there were 2 because we had 4 points. As I already said, if one field is diagonal, so that it modifies the weight of loops turning around that point, then at least we will need to have a pair of legs from a non-diagonal field that encloses it. So here are some examples. So for example, here's one example of this enclosure. Okay, now to arrive at 3-point functions, a bit paradoxically, you have to move over via 4-point functions. At least that's the route that we have been taking. So 4-point functions are difficult in this problem here because we don't have the usual differential equations that you would have in a BPZ-like setup. So why don't we have this? Well, it's because to get those differential equations, you need a degenerate field. But we only have degenerate fields that make the S label vary. The degenerate fields that would have a different R label, they are not present in this theory. So there is some way of dealing efficiently with the S label, but not with the R label. And so for that reason, we cannot get those differential equations that one is used to having in minimal models. So instead of that, we will then move to the conformal bootstrap technique. And then we will take advantage of 2 things. One thing is that the degenerate field that we do have, say the smallest one, V13, it generates this interchiral symmetry. And the second thing that we will take advantage of is the global ON symmetry. So let me show you a bit how this would look like. So imagine now that you want to have a 4-point function, say of non-diagonal primaries, and you want to write its S-channel decomposition in terms of conformal blocks. So you would then have something like this. You would have 2 sum over all those degenerate fields with the S label, and you would have a double sum over all the non-diagonal fields with convenient G's, which are products of left and right moving conformal blocks. And those blocks, they are known from the Samologikov recursion relations. You need to take a little bit care here because there is something slightly logarithmic going on over here. So some of those blocks are actually logarithmic. But nevertheless, you have such an expression here. So that gives you a lot of fields.
The diagonal fields of momentum P, they kind of close among themselves. They don't participate in this OP.
No, they don't participate here in general. So now the degenerate shift equations using this B13 field, they will actually relate. So they will fix the quotients of these 4-point structure constants T when S is shifted by 2 units, both over here and over here. So what we could do is that we could define some bigger structures that take advantage of these known ratios and couple together all the S that are just shifted by a multiple of 2. And then those guys we will call H, and they will be called interchiral blocks. And then you get this simpler expression here, and where you see now that this sum over S has been curtailed so that it operates just on an interval of length 2. So this is big progress. For example, if you want to do numerical conformal bootstrap, now you have a lot less fields to bootstrap. So the idea is then you should solve the crossing equations. If you can, you should do it analytically.
But you still have infinite many terms.
Of course, we still have infinite many terms, so it's complicated stuff. So yeah, and we know the spectrum. That's very important. So since we know the spectrum, then solving these crossing equations, of course, it's a very technical thing to do. It requires a lot of work, but basically you see what you should try to do is to say, let's cut off the max conformal weight. Let's say that we only look at such fields that have a conformal weight less than, say, 100. So then we have a finite number of fields. And then we look at those equations here, and then we evaluate them in various points so that we have enough equations so that we can solve for all the unknowns. So it's basically a question of solving a linear system when it comes this far. But of course, a lot of technical ingredients go into it. So now these solutions, of course, they could be analyzed in terms of the global symmetry. So for example, the role of one leg here is that it carries the fundamental representation of ON. So you can think of it in terms of multiplications of Young diagrams in ON. But to really fix the solution space for the conformal bootstrap, it's better to think of a certain characteristic that we call signature for the combinatorial map. So this is a helpful thing to constrain the solution space. And then if we are good, then we can get a unique solution. So there's a conjecture motivated by a lot of computations of 30 correlation functions with small values of R, which is that each solution to those crossing equations, it gives a valid correlation function in the conformal field theory. Okay, now for the sequel, I will need to, maybe in this precise place, one does not need to recall anything about any special function, but there's one special function that will appear here that is called the Barnes double gamma function. So with a parameter beta and argument x, okay, it's given by this terrible integral over formula here, when the real part of x is larger than 0, and constrained to a certain interval so that you can get any x that you want by using those two shift equations. It's also related to this epsilon function.
Just a question, Q is greater than 2, is that correct? In your notations.
And Q is in general complex.
Yeah, but if it is real positive, greater than
If it's real, then
just to make contact with
okay, so
other-
of course one thing that's important here is that this Q is not the Q of the Potts model or anything.
no,
It's
it's
another
Q of XG.
Yeah. So let's see. So is it?
If beta is real, then
What is the
must be
minimal
wrong.
value? Yes, that's okay.
Yeah. Okay.
The condition is real part of beta spread larger than positive. That's the domain.
It's not particularly helpful, I think, to think of beta being real. It's better to think that it's just some complex number. Okay. Now I want to define a very important object in this talk. It's called CREF. It depends on 3 pairs of RS indices, and it's a product of 8 of these Barnes double gamma functions. So written very compactly like this. I'm going to make this definition here when I have 3 non-diagonal fields. But I could also define the same object in the case when I had diagonal fields. In this case, for example, if I have this momentum P, I will just convert P into a pair of RS labels with R equals to 0, sort of transcribing that a diagonal field does not insert legs and putting everything on the S index. And then I would denote that CREF as CP1, P2, P3. The first remark that I can make now is that this CP1, P2, P3 actually is nothing but the imaginary DOZZ formula. Okay, so that shows that sort of sacrificing the R index in this formula here, you get back to an object that you know. But then there's another remark, which is that by doing all this bootstrap work, we have observed the following thing. So if you look at the 4-point amplitude in the ST or U channel, it turns out that it can be written as a product of 2 of these CREFs times a certain quantity DRSX, which turns out to be a polynomial in the loop weights. Okay, so obviously a polynomial that's much simpler than the rest. So it somehow shows that there's a particular sense to this CREF that somehow must be important. But then the real sort of, idea came when you look closer at this probabilistic paper that came out in 2024, in which they actually compute C222. Okay, so once you sort of fix normalizations in a way that's compatible with what I have said until now, it turns out that the C222 is the CREF 101010. So from these 3 observations, it starts getting tenable to say that maybe the structure constant that we are looking for is somehow just the CREF. But you should not forget the other paper, the one from 2016, that taught us that you have to be very careful when you discuss 3-point functions, because you have to normalize them correctly in terms of 2-point functions. If nothing else, to get rid of this coordinate dependence. So we will define an object which is called omega. So omega of 3 fields, 1, 2, and 3, that will basically be the CREF, but it will be normalized by the square root of the corresponding 2-point functions, but also by the partition function. And if you stare at this formula for about 15 minutes, you will realize that even if you apply it on the lattice, somehow all non-universality that could be due to the particular way that you realize operator insertions on the lattice that has somehow been taken care of. And I mean, this defines a good universal quantity. And in this writing, zero means the identity field, and the identity field is degenerate, so I will have to treat it like this, as I said before. So this omega is the 3-point object. So here is a transfer matrix computation. Here we are on a cylinder of width 5, 6, 7, 8, up to 13. And we compute the probability that two legs coming out on the bottom of the cylinder will be such that one of the legs will go to two prescribed points somewhere in the middle, and the other of those two guys will go up to the top along with the last leg that was left over. Okay, so we have on the cylinder, we have a regularization of this C222 correlation function, and we can extrapolate in the size, and then we get those black points. And the orange curve is the analytic result. So it looks like this works pretty well. And here is n the weight of an ON loop in the dense phase and in the dilute phase. So here's the general transfer matrix setup. And now the big issue is how can we deal with any 3-point function in such a setup and compute a lattice regularization, because we need to know if our conjecture is true. Let's take a loop model on a square lattice with these weights here. They are known by integrability. The partition function is this. And we have 3 regions, one on the bottom, one in the middle, and one in the top. And the idea is basically to send in some lines in R1, make some of them go through R2, but the others go directly to R3, and the others left over from R2, they go to R3. And it has to be done in a way so that we compute then a sort of modified partition function, Z1, 2, 3. And then we will compute also these other partition functions. You see here that now we are having something a little bit more complicated with this Z202 and Z220. They are now different because we treat the point in the middle a little bit differently from the points on the bottom and top. And this we also need to think about carefully. Okay, so in the end, we will get this C123. And now the question is, if I take the width of my lattice, if I first take an infinite cylinder, m goes to infinity, and then I take the limit of my finite size results to infinity, L goes to infinity, could we then hope that this will give omega 1, 2, 3 in agreement with the formula? So there's a very delicate part here that I cannot give full justice to, because I'm flashing some formula here. It's super difficult to treat this case with non-zero spin, so the S index. Okay, but after everything has been said and done, it boils down to sort of putting labels on your legs and making sure that you get through all possibilities and you weight them correctly with these exponentials. Okay, so let's just imagine that this has been done. So we have this transfer matrix. We compute this Z1, 2, 3 using some representations of this Jones-Temperley-Lieb algebra, but with some extra information in which we keep track of labeling of legs and where they go. And then we have some very clever operator in the middle that does something particular. Okay, so details you can look at in our paper. So now I think I've said everything. So here is what it amounts to. So if you do finite size, say here for L equals 8, 9, 10, and 11, you get a pretty large scatter of the points, but you can extrapolate. And then you get these sort of greenish point here, and you see that they fall well on the curve of the analytic result. So we have great confidence that that this conjecture is the sort of final word on 3-point structure constants in loop models.
Now that you have a guess, analytic guess, we'll try to put crossing analytically somehow, given the answer. Or...
Oh, you can trust us to try all kinds of things right now. So in general, but I mean, okay, so the analytic formula for this C-ref in the study of 4-point functions, that was something that was already there. So the really outstanding question is, how do you, if you know the 3-point structure constant, how do you get the 4-point structure constants? So there's something strange going on here, because you can actually have several fields with the same conformal weights. So there is some problem for just stating that. You cannot just state that you believe that 4-point structure constant should factorize into 2 3-point structure constants. This is the main obstacle for solving this problem completely. Okay, now I have a few minutes left. And in this few minutes, I wanted to make a remark that could have made Slava happy if he had been around, but maybe he's on Zoom. So on complex CFT, but it might also be interesting for some other people. Okay, so in a paper with Gorbenko and Zan, Slava has shown that you can give sense to CFT for the ON model when n is real and larger than 2, a bit surprisingly at first sight. But there's a trick to it. You need to take the coupling constant k to be complex. So you have complex CFTs. And they basically occur because when first you take real n less than 2, and if you move towards 2, then you have a tri-critical and a critical point that can somehow annihilate. And then they will move out in the complex plane to form a pair of complex conjugate CFTs. Okay? You can do the same thing for the Potts model. You can actually get a critical conformally invariant 5-state Potts model if you want, at the expense of taking some coupling constant complex. If you want to do that, it's crucial to start from a lattice model that contains both fixed points, both the critical and the tricritical one. And there's a paper by a group of 5 Chinese people, Tang, He, and Shu, that have shown that how to do this for Q integer. And there's another paper with by me and Kai Bieser that shows that if you take a convenient loop model, not the one that I have shown you, another one, it really needs to live on a triangular lattice and have 3 spin interactions, because otherwise it cannot do the job. And that loop model can realize a complex CFT for Q equals to any complex number. Now, the question is, in this precise context, what about our formula for 3-point structure constants? And now it turns out that in this paper by Tang, He, and Shu, there are results for 3-point structure constants. And they mainly promote in their published paper, such 3-point structure constants that can be obtained either directly from Dovzhenko-Fateev or some reasonable analytic continuation thereof. But they also have in their drawers, they have some unpublished results for some of these non-diagonal fields. And I have exchanged a bit with them over email, and they have showed their numerical values. And they agree nicely with our formula. You just plug in and you find their complex 3-point structure constants analytically up to the conjecture. And then I wanted to also remark on the theme of the seed series here, so spanning trees and forests. So if I take now not the ON model, but the POTS model, and if I send the number of states to 0, then I can get uniform spanning trees. Okay, so they are in the loop model setup, which loops on the square lattice that looks like Temperley-Lieb loops that go everywhere, and there's just one single loop. And that loop has one tree on its outside and a dual tree on its inside. And then you could ask, what can we say about 3-point functions here? So for example, let's start with this 1, 0, 1, 0, 1, 0 guy. There's a little factor that comes out by the normalization because you had one 3-point function upstairs and you have square root of a product of 3 2-point function downstairs. So there's going to be one loop in each configuration, and in the end you get 1. Okay, and that shows you that if you take 2 points or 3 points, they will always belong to the same loop because there's just one loop. Okay, so that looks at best like some kind of sanity check. But now you could maybe go on. You could say, okay, let's try one of the other structure constants, 2, 0, 1, 0, 1, 0. If you evaluate it, you definitely get some non-trivial number. The question is now, how do you interpret it? Okay, so that means you have some neighborhood where you have 4 loop ends going out, and then you have 2 neighborhoods where you have 2 loop ends going in. So what you could imagine is that in your tree, you have 2 long branches. And then somewhere you look at the junction of those 2 long branches. And at that junction, you will see those 2 branches going out with an inside and an outside. So that gives you a total of 4 legs. So that gives you this thing here. And then you could put another point at the end point of each of the branches, which will then correspond to 2 legs. Okay, so you're sort of asking about a uniform spanning tree. What's the probability that I sit at the junction of, that one point sits at the junction of 2 long arms that extend to the other 2 points? Now, to actually get this result, then you will have to normalize by this product of 3 2-point functions. And now those 2-point functions, they are also non-trivial because some of them will involve 4 legs. But if you do this, I have this prediction for trees that you can measure, you can get such a number here.
You make a drawing on the board, please.
I can try. So here's a tree, here's a point, here's a point, and here's a point. And then ideally I should have some other color. Yeah. Now if I draw the loops that turn around this stuff here, going to look like this. So you have a neighborhood here with 4 legs, 2 legs, and 2 legs. And then you have to think about again what of those normalizing factors are, but that's one of the way to work this out. And then all generalizations thereof. So there are 2 minutes left, so I can wrap up. So the conclusion is that we have an analytic prediction for all 3-point structure constants and loop models. For degenerate operators, it agrees with Coulomb gas. But the Coulomb gas was nice in the 1980s, but it's sort of not a fully satisfactory approach to loop models because there are things that you cannot compute in the Coulomb gas. And one thing of it is the DOZZ formula. And the reason that you cannot get the DOZZ formula really from Coulomb gas is it has something to do with charge neutrality. Okay, so the DOZZ formula shows you that you don't need a total charge of 0 for a 3-point function to be non-vanishing. But for non-diagonal operators, our formula also goes beyond the DOZZ formula. So it looks like sort of the Coulomb gas can sort of be put in some kind of garage, and the DOZZ, or the imaginary Liouville approach, could also be put in some kind of garage. I mean, they are good enough for what they can compute, but they are not good enough for everything that you want to compute. And so the question is, what kind of theory is it now that, what kind of label should we attach to this theory that contains such a formula? We have a precise link to results from the lattice model via this transfer matrix construction. And there are many outstanding questions. The first, obviously, is, can our conjecture just be proved analytically? Maybe the uniform spanning trees are actually a good testing ground, okay? Because for uniform spanning trees, you can do many, many things with determinants and things like this. It's a free theory, it's free fermions. So maybe one could try to prove, for example, this formula here independently using fermionic techniques. There's an outstanding question about what is this operator that I had in the middle and how is it related to the paper here that is cited. Also, another thing is that if you look carefully at how I related my transfer matrix to the 3-point structure constant, something that looked like form factors appeared. Form factors could maybe be computed using integrability. But the biggest problem, in my opinion, of all is how do we now get 4-point functions? Because we know from general CFT ideas that we need really to have 4-point functions in order to claim a full solution of some theory. So yeah, that's it. Thanks a lot.
Thank you very much. Questions?
Question.
Go ahead.
Just the O2. When you mentioned the O2 briefly before, you said there was a link to broken legs or broken.
Yes.
So what did you mean by that?
So what I mean is, so I'm somebody who's obsessed by defining things properly on the lattice. Okay, you have this square lattice here. Okay, it's wrapped in a cylinder. So this is identified with this, and then if I want, for example, this 2-leg thing, then I would insert one leg on the bottom. Say on those two sides, I would take them out on the top, and then in the middle, I would take one edge and I would break it like this, and I would declare this to be one endpoint and this to be one endpoint. My endpoints here. So the object that I want to look at is something like this, where one of these legs here connect to one of those points, the other point connects up to the top, and the other guy here goes right to the top. Okay, so that gives me a very specific definition for what's going on in the middle. I break here one leg. If I needed more points, I would break several legs. And then I define this correlation function.
Questions?
Can you just briefly comment on the modification to the Potts case of the guest formula?
Yes. So basically, you don't need to modify anything at all. The only thing that you need to okay, now I need to do 2 fingers, but 28 times. That's a good exercise, but I need to get back to this first slide here. Okay. So for the Potts model, there are some things that are just ever so slightly different here. For those degenerate fields here, you have S equal to any positive integer. And then also there is in the POTS model, you can not only insert curves, but you can also insert a cluster. Okay, so this is a well-known thing for specialists on the POTS model, that suppose if you want a cluster to propagate, say on a cylinder, it doesn't mean that there's a pair of boundaries that propagate, right? Because almost surely the cluster will wrap around the cluster when it propagates. Okay, so there's a specific operator that corresponds to inserting one cluster, and that is that has labels 1/2 and 0 in this setup. So once you operate just this modification of this set of operators, it's a plug and play formula. Okay, so you just plug into it.
I seem to remember there was some ambiguity in interpreting in the operator spectrum when you try to identify the representations of the ON of the partition function. You try to figure out what's the degeneracies there. Was that completely solved, or was that I misremembering some facts?
Can you remind me a bit more specifically what you were referring to?
Remember that there were many.
Paul has a telepathy
Yes,
connection.
so what you're talking about is the fact that there are much more when invariant tensors for a given 4-point function, and there are solutions to bootstrap equations.
Right.
And it is not solved, but it can be solved in the facts. You can change it.
Uh-huh.
So the outcome of this is that when it's really not enough to constrain the bootstrap, you need different, which is the combinatorial maps. To count solutions to the bootstraps, you cannot just look at O and symmetry. It's a different thing. It's a combinatorial object.
So this is in particular where this signature thing comes in.
More questions? Not, let's thank you. We resume at 5.